Today, we're going to talk about a huge, and I mean huge, revolution in engineering that's happening all around us, mostly unseen. It's the story of how we went from solving problems with pen and paper to predicting the future with incredibly powerful computer simulations. I mean, really think about that for a second. How do you know a jet engine will work at 3 times the speed of sound? Or how a bridge will hold up after 50 years of rain and traffic before a single bolt is in place? Well, the answer is in the digital world, and it has completely changed the game for how we design. Well, everything. So here's how we're going to break it down. First, we'll look at the old way, the world of neat and tidy formulas. Then we'll jump into the raw computational power that just shattered those limits. We'll see how engineers can now predict when things will fail decades in advance, how they're creating designs that were once pure science fiction, and finally, what this new reality really means for all of us. All right, so let's start at the beginning. For over 100 years, engineering was all about the elegance of the equation. It was a world of pen, paper, and really smart people with slide rules. This slide really shows the 2 different worlds we're talking about. On the left, you have the formula approach. Think of it as a perfect, clean recipe. If your ingredients are simple and you follow the steps, you get one precise, correct answer. But on the right, you have the simulation approach. This is for when reality gets messy. It's less like a recipe and more like using a supercomputer to try 1,000 tiny variations until you land on a solution that works. And don't get me wrong, that old analytical toolkit was powerful stuff. Engineers had these standard, trusted formulas, like the SKF method for bearings, that could calculate how long a part would last, but only under very specific, ideal conditions. These formulas literally built the modern world we live in. But that's the catch, right? The real world is anything but clean. It's got weird vibrations, temperature swings, all sorts of complex forces that a single equation just can't handle. So what happens when a problem gets too messy for a formula? For a long time, the answer was basically build it way stronger than you think you need and cross your fingers. But that was all about to change. And that change, of course, was the digital revolution. This is where computers came crashing onto the scene, not just as fancy calculators, but as virtual laboratories that could finally handle all that real-world messiness. So how do these numerical methods actually pull this off? Okay, imagine trying to find the exact area of a weird blub-shaped puddle. A single formula for that? Almost impossible. But what if you just drew a grid over it with a million tiny perfect squares and just counted the squares inside? That's the basic idea. You take one giant, impossible problem, you chop it up into millions of tiny, easy ones, and you let a computer do the grunt work, getting closer and closer to the right answer with every little step. And the process itself is actually pretty intuitive. First, an engineer builds a digital model of the thing they're testing. Then the computer makes a starting guess, runs a calculation, and checks how close it is to reality. If it's not quite there, it tweaks its guess and does it again, and again, and again, thousands or even millions of times, until the simulation is practically indistinguishable from the real thing. This iterative power has handed engineers a toolbox that would have looked like pure magic just a generation ago. For instance, with something called finite element analysis, they can take a complex part, like a gear, and digitally break it into millions of tiny pieces to see exactly how stress flows through it. They can use algorithms that actually evolve a better design, or machine learning that listens to a machine's vibrations to predict a failure before it happens. It's incredible stuff. Okay, so we've got this amazing new toolbox. How is it actually being used? Well, let's look at one of the biggest challenges in engineering: figuring out when and how things are going to break. Let's start with something small but essential: a ball bearing. These things are in everything, from your skateboard to a massive wind turbine. Now, a simple formula can give you a rough idea of its lifespan in a perfect world. But what about the real world with all its bumps, heat, and less than perfect lubrication? Well, to solve that, engineers throw the whole digital toolbox at it. They can simulate the bearing in insane detail, seeing the exact stress on every single ball inside. They run thousands of different simulations to account for microscopic imperfections for manufacturing. They can even model the sound waves, the vibrations the bearing makes to listen for the very first signs of trouble. And here's the payoff. We've gone from a vague estimate to an incredibly precise prediction. Engineers can now simulate the entire life of a component and see not just if it will fail, but exactly how and when, sometimes decades into the future. That makes everything safer and more reliable.
But it's not just about things that snap. What about the slow burn problems, like rust spreading across the steel beam, or concrete slowly breaking down over 50 years? Those are incredibly difficult to predict with a simple formula. This is really where these numerical methods are just amazing. Instead of one formula, engineers build a living, dynamic simulation. They can model the chemical reactions of corrosion spreading over time. They can build algorithms that track thousands of tiny variables, like humidity and surface texture, to predict how a structure will degrade, giving us a clear picture of its future.
But predicting failure is only half the story. Maybe the most exciting part is how these tools are being used to create things that were simply not possible before, leading to some truly optimized, futuristic designs.
This is pretty much the holy grail for a lot of engineers. How do you make something as strong as it can possibly be while using the absolute minimum amount of material? It doesn't matter if it's a car part, an airplane wing, or a medical implant, that strength to weight ratio is everything. To crack this problem, engineers are using tools that are frankly mind-bending. There's something called topological optimization, where an algorithm starts with a solid block of digital material and just carves away anything that isn't carrying a load. What's left are these wild, almost alien-looking structures that are insanely strong and light. Or they use genetic algorithms, which literally breed thousands of designs together, generation after generation, until the best one evolves. And this is where the paradigm totally shifts. The computer is no longer just a calculator. It's a creative partner. It's exploring a universe of possible designs, millions of them, to find solutions that a human engineer relying on just intuition and old formulas could probably never even dream up. So, when you put it all together, what do you get? You get a fundamental change in what engineering is even capable of. A shift from what was once just theoretically possible to what is now totally practical. I think this chart just says it all. The old analytical methods were great for the problems they could handle, but there was a pretty low ceiling on complexity. Numerical methods? They've just blown that ceiling wide open, letting us solve problems that are astronomically more complex and way more true to life. So why does all this matter to you? Because it's the reason our cars are safer in a crash, our airplanes use less fuel, our buildings can withstand earthquakes, and our phones are more powerful than the supercomputers of yesterday. This digital revolution lets engineers see the invisible, test the impossible, and, in a very real way, predict the future. And that brings us to one last really fascinating question. We've gone from simple formulas to simulations that can model just about anything, from a single protein to an entire galaxy. So with all this incredible predictive power now at our fingertips, what's next? What's the one big problem we should point this thing at and solve?